In our first question, we must express the equation in a certain form. Of course, this is completing the square. I'll just write out our formula there and we'll get started. We have P and Q, which are constants, and so we will simply set out with that formula and simplify it down. A fairly simple question, 2 marks. And we put our constants together, and that's pretty much it. So x minus 4 in brackets squared minus 5. Hence denotes that we are using something from a previous part of the question, generally the answer from part A. So find the exact solutions for our equation, but just be careful, it's also equal to 1. There's a little different part there. So essentially from this point, simplify it, cancelling items on both sides, and when the terms have been cancelled, you should just end up with x. So we have x is equal to 4 plus or minus root 6. In our second question, we are given details for an arithmetic progression. Keep note and have your formulas in front of you if you're not entirely sure when you're practicing these questions. So your end term is a plus n minus 1 d times d. And so in this case, we have a plus 12d is equal to 12. And the sum is n over 2, then 2a plus n minus 1d. So the 29 comes from 30 minus 1. And we're given the answer for both. So obviously we have to use simultaneous equations because we have unknown values. So we're going to equate them in some way to help us out there. But so first of all, they must solve the sum. So just multiplying it out. So it looks like we're going to be multiplying our first formula by 30. I'll just rewrite it then. So we've got the same sign, and we can subtract. So the 30a will disappear. So we can solve for d, in which case we get minus 75d is equal to 375. So d is equal to minus 5. From there you can substitute your minus 5 back into the first formula perhaps, into either, and you'll get a. And a is of course 72. So d and a have been solved, and the third part of this is to find the sum of the first 50 terms. So we're going to reuse that sum formula. 50 over 2, 2 times 72, plus 50 minus 1 is 49, times minus 5. The final answer is minus 2,525. In this next question, we're looking at the binomial expansion. We have a coefficient of x to the power 4 for a and a coefficient of x squared for b. So now we'll do our expansion. So we have 5, 2. So this is to do with combinations. On your calculator, you'll have 5C2 perhaps. It might also be an NCR button. Of course, have your formula in front of you if you're not sure for the binomial expansion, but just practice enough of these questions and you just memorize it through that practice. You may also use Pascal's triangle, or just try and remember the ascending and descending exponents of this particular formula, and it will be more familiar to you. So a is equal to 80k to the power of 4, and b is 24k to the power of 2. It is given that a plus b is equal to 216, so we have those values. Find the possible values of k. So we'll simply put in our values there. 80k to the power of 4 plus 24k squared is equal to 216. And now simplify it down. Pretty sure we can divide by 8. So we'll get, 10k to the power of 4 plus 3k squared minus 27. So from here, we will factorize our equation. So 10k to the power of 4. So we're going to have like 5k squared and 2k squared. And then 27 is 9 times 3. So it fits in nicely. So k squared is equal to plus 3 over 2 or minus 9 over 5. So we have our value of 3 over 2, but just make sure that it's k is equal to root. So plus or minus the root of 3 over 2. And they are the possible values of k. In question 4, we must prove that this identity is equal to the right-hand side, which is minus tan squared theta, and in brackets 1 plus sine squared theta. So we're going to multiply across on both sides. So with this kind of question, you will see that you have to multiply across because we want to get the same denominator. We want to simplify it down in some way. We also know that we're going to require our identity of tan data equals sine data over cosine data. So that's going to come into something later on. So I'll multiply everything out now. One thing to remember with this, actually, as I'm doing it, is you have sine data squared. In this case, you have cubes and also the power of 4. Just keep in mind that the angle of data, which is the symbol there, is what is affected. Sine itself is just a function, so it wouldn't be squared or cubed itself. So it's a kind of a shorthand that we're doing here when we have sine squared data. In fact, it probably should be more like sine data squared. Just to note. So I've cancelled out some parts there. And we're getting to the end of it now. So cancel out those parts. So you know that our second identity from grade 11, cosine squared data is equal to sine squared data minus 1. Just rearrange that original identity. I've also just multiplied it by a minus sign there. So by multiplying by minus 1, I changed the 1 minus sine squared data to sine squared data minus 1, which is in fact cosine squared data. So we're going to factorize our terms there. You could, of course, divide out your two numerators separately with cosine squared data, but I've just put it together in one go. And from there, of course, sine over cosine is tan, so you get your answer. So minus tan squared theta, and brackets then 1 plus sine squared theta. In part B of question 4, we're given what looks like almost the same. It's a very similar right-hand side part to our question A that we had. So have a quick look back at that if you need to. So we had minus tan squared theta. So it's changing the sign there. It's a very small little difference that could catch you out. So again, just thinking about our identities, sine squared theta all over cosine squared theta is tan squared theta. And you can then convert cosine squared theta back to 1 minus sine squared theta, which we did in the previous question. And you'll see that they cancel out then. So sine squared theta is equal to 0. And really it's sine theta squared. So on our graph, you can draw a little graph there. you're going to have one value or more. And we're using radians, and it's between 0 and 2 pi, so a full periodic pattern. So it's 0, but it's also going to be halfway, so pi. So our two answers are 0 and pi. So you can keep your calculator in radian mode, as we now have a sector question. We have a triangle and a partial part there. So let's have a look. We're given data is pi over 6, and we have to find an exact area for part A in terms of R. Your formula for the area of a sector is half times data times radius squared. So we put those values in, and we've got our answer of pi r squared over 12. From there, I'm going to look at BD and AD specifically, the lengths. So we have pi over 6r. Again, think of your trigonometry here in terms of the sine. That would be 1/2 r. And AD the same, but in this case it's a cosine. So it's the same pi over 6r, but we get root 3 over 2r. So just keep in mind there that r is the hypotenuse of that triangle. So the area of our triangle is half times base times height. So there were our two lengths there anyway. And we get root 3 over 8 r squared. So that's our triangle, and above, of course, we had the whole sector. The area for the whole sector was pi r squared over 12, and the area of the triangle was root 3 over 8 r squared. So we subtract them to find the answer if we had those unknown values. So in part B, we're given a change. So the length of BD is now root 3 over 2r, and we need to find the perimeter in terms of r. So this change is going to affect the value of our angle data, and we're going to also have to find the length of the arc from B to C. So once we've got those two bits, we might be okay. So BD was root 3 over 2r, and we now find data. The inverse of sine is equal to opposite over adjacent, which was root 3 over 2 all over r, and so the answer is pi over 3. So data is pi over 3 now. From there we can find the length of the arc, which is r times data, the angle times your radius, which leaves us at pi r over 3. Now, back to AD. You can do with your trigonometry, cosine pi over 3r. And check that, you'll see you get half r. So 1/2 r, that's half the radius. Now, you'll know that these questions are not to scale and that kind of thing. So it seems like a little bit of a trick. But AD is half r, so DC is half r as well. We have to have one full r, one full radius. So then we can put our three details together. You had your root 3 over 2 r. You have your pi over 3r and your half r. They're the three sides of that shape for the perimeter of BCD. Once again, you can see the three sides of BCD there. Question 6. We are dealing with functions. So we have a rational function, and our domain is x is greater than 2, and we need to find the inverse. So again, instead of fx, you can revert it to y, same thing really, and start doing what you got to do with this question. So we're multiplying across x squared plus 4 from the denominator. Then we're going to multiply out the brackets, expand. And then we're going to just continue on, simplify, and generally you have to factorize as well when you have the same variable. So in this case we have x squared so pop x squared outside, and we have minus 1 plus y, or y minus 1. And then we can divide both sides by y minus 1. We have a lot of minuses, so we can just turn that around, because we have an x squared, so it's going to be a square root, which can be positive or negative. So the final answer for x would be root 4y plus 4 all over 1 minus y. But that's, make sure to convert back to the final answer. So the inverse of f of x is root 4x plus 4 all over 1 minus x. Be careful with that detail. Part B of question 6, show that 1 minus 8 over x squared plus 4 is equal to our original rational function that we just looked at, and also hence state the range of f. So we're going to rewrite 1 as x squared plus 4 all over x squared plus 4. So getting the same denominator. So little algebraic tricks like this. So for the numerator, x squared plus 4 minus 8 was of course x squared minus 4. When you test a number of values for the value of x in our function, you might see a trend. So 1 minus 8 over x squared plus 4 is 8 over 8, which is 1 when we have x as 2. So 1 minus 1 is 0. And then let me say x is anything else. We'll say 10. So 8 over 10 squared plus 4 is 104. So it's going to be a fraction. It's getting smaller, we say, as the number for x, as the value of x gets larger. So it's towards 1. So our range is between 0 and 1, essentially. Our original domain was x is greater than 2, and we have now a range for f of x. So when we say there's a composite function of ff, think of it as like f of x. And you know it's going from fx to f. So f of x is, we'd say, going from, well, the range is 0 and 1. And for our original f, it's a domain of greater than 2. So it's not included. The range of f does not include the domain of f. In question 7, we have a diagram with a curve and a line, and they intersect at points A and B. So they intersect, meaning that we will equate them, make them equal to each other. And from there we can solve for x, hopefully. So from there I can cancel that root. So to the power of a half is a square root. So it squares the other side. Multiply all that out. 1/4 x squared plus half and half is x plus 1 squared is 1. And from there we can put our bits together. So 1/4 x squared minus 2x plus 3 is equal to 0. Multiply it up, multiply it by 4. So x squared minus 8x plus 12 is equal to 0. So x, 6 and 2. So we got boundaries of 2 and 6 for x values. And we're going to find the y values now as well. So just substitute it back into the easiest equation, perhaps. The line, generally. So we end up with 2 and half, 6 is 3, so 4. So the coordinates for A was 2, 2, and for B was 6, 4. That's our final answer for part A of this question. Part B, we have to find the area of the region enclosed between the curve and the line. A main thing here is to take note of which one is above or which one is below. And we're going to integrate, of course. And we have our boundaries of 2 and 6 for the x-axis. It's also a trapezium, and triangle, but it might be a bit too much. We'll just do it this way. So we'll take away the curve, well, actually do the way around, the line from the curve. And when we've integrated, we will substitute in our values for 6 and then 2. So 1/2 over 3, 3x minus 2, 3 over 2 times 3. So it's a chain rule there. And then I'm just going to simplify that part first before I do the line. So 2 over 9, 3x minus 2 to the 3 over 2. And then our second part for the line, 1/2 x, so be 1 over 4 x squared plus x. And all of that with 6 and 2 as our limits. And so you'll plug in 6 to all of that and plug in 2. Do it on the calculator in 2 steps. And you'll get 4 over 9. In question 8, we have a curve and there's a transformation. So in the brackets, there will be horizontal transformations, and outside we have 4 signs. So the 4 is a vertical transformation. We'll deal with the horizontal ones first. Just think of bid mass if you want. So the first one is a translation of minus 30, so that's plus 30. On the horizontal x-axis, second one's a stretch. Again, 1 over a is the way you've been taught for like the scale factor for the x-axis. So it's not 1/2 of it, it's a times 2 stretch. And for the y-axis, of course, much more straightforward, it's times 4. Spend a little bit of time looking over the transformations from functions as well, but from Unit 5 you have trigonometry. It needs a little bit of isolated work sometimes to check that kind of stuff. So we have a second part where we're given our curve and it's equal to 2 root 2, and we're given a boundary of 0 to 360 degrees. So make sure you change your calculator to degrees, and we're going to find the exact solutions. So if we divide both sides by 4, let's say we get our inverse sine for 1/2 x minus 30 is equal to 45 degrees. And from there we can find our value for x, or more than 1. So again, 1/2 x is equal to 75. So x is equal to 150. Now draw your sine wave. And you'll see where 45 is. So 45 is in between, the first notch there. And of course, if you look, you can see it has a similar value, same value, just a little bit on just in the second part there, so 135. So within the periodic pattern from 0 to pi, we have 45 degrees and 135 degrees. We'll now just do that second part. So 135 plus 30 is 165. So x is equal to 330. And those two values do fit within that boundary. In our penultimate question, we have an equation for a circle. So we're looking at coordinate geometry. We've defined the coordinates of the center and the radius and the lowest point. So I'll draw, well, I won't draw actually. I'll put in a little graph there for the second part. So find the coordinates. We can complete the square. That's the way to do that. So x squared plus 6x. So x plus 3 minus 9. And then the same for y. Y minus 2y. So y minus 1. So minus 1 squared minus 26. And we have our coordinates there. So we have minus 3 and plus 1 are the coordinates for the center. And put your constants together and you get 36. A nice round value of 6. So 6 squared. 6 is our radius. And the lowest point, the easiest way to do this is just put in that center point. So it's just a sketch, it doesn't have to be that accurate. We know the circle goes around that. And so where's the the lowest point of the circle? We'll just think the radius is 6, so we'll just go down 6. So from from 1 to -5 is 6 steps, we'll say. So that's our point there. So the lowest point is -3, -5. On to part B. So find a set of values for the constant k. So we're given an equation y equals kx minus 5 where it intersects the circle. So it intersects the circle at 2 distinct points. So that gives us 2 bits of information. We're going to be using the discriminant, b squared minus 4ac is greater than 0. And also y is kx minus 5. So we're going to replace y in our equation of the circle. And there's 2 of them. And that's pretty much this. But it takes a little bit of practice to work your way through these questions when you get the k and the unknown value. It happens in Unit 1 in quadratics, you have it in Unit 2 with functions, and then later units like this, where you have to do a lot of algebra. And be very careful with the details, because there's often not a lot of marks for follow-through. So we want to basically get our ABC, or ax squared plus bx plus c. We want to get our squares on one side, then the x, and then our constants separately. So in green there I've just highlighted the x's. So I have a kx, but we're going to put it together in some way. And then the first 2 terms have an x squared. So it's 1 plus k. So I just put it like k minus 1. X squared plus 6 minus 12k to the x. So this is a factorizing bit there. So the first 2, like the k minus 1 and the 6 minus 12k, I've just factorized there. They have a common term. And now b squared minus 4ac and multiply it all out. 144k squared minus 144k plus 36. 36k squared minus 36 is greater than 0. So cancel out your 36. We'll end up with 108k squared minus 144k is equal to 0. So k is equal to 0. In that sense, we also have divide 144 on both sides and square it, you'll get 4 over 3. So k is less than 0 and k is greater than 4 over 3, because we're dealing with, of course, a set of values for the constant. So, on to the final question. The equation of a curve, we have a second derivative of 6x squared minus 4 over x cubed. There's a stationary point, and we've defined the nature of the stationary point. So we're given an x and y value. So given the x value, we can substitute that in. So 6 plus 4 is equal to 10, which is greater than 0, so it's a minimum. So that's it, basically. That's the nature of that stationary point. Next part. Find the equation of the curve. Okay, so we're going to find our gradient, so dy over dx. So we're going to integrate the original equation of the curve that was given at the top. So 6 over 3, x to the power of 3, minus 4 over 2, x to the power of minus 2. So we simplify that, we get 2x cubed plus 2 over x squared, or 2x minus 2. You can use whichever one you want. So 2x cubed plus 2 over x squared plus c. So I'll just solve for c here. So dy over dx. So c is equal to 0. And now we can do our equation. So y is equal to, so we're going from the second derivative to the derivative dy over dx to now y. So it's 2 integrals. So That's what I'm writing right now. Plus, at the end, an unknown value, a, we say. Okay, so we had a y value of 9 over 2 is equal to a half, and then plus 2, plus 0, and so a is equal to 2. So y is equal to 1/2 x to the power of 4 minus 2 over x plus 2. And that's our equation of the curve. So show that there are no other stationary points. So we're going to look at our derivative. We were given a stationary point already, so x was minus 1. So let's focus on that. So dy over dx we have already is equal to 2x cubed plus 2 over x squared. So again, make it equal to 0. So that's where a stationary point is. Multiplied out the x squared from the denominator to get x to the power of 5 on that term. So 2x to the power of 5 plus 2. And of course the x squared cancels itself out, times 0. So x to the power of 5 is equal to minus 1, so it's minus 1. In the last part of our last question, we're looking at the rate of change. So the rate of increase of an x-coordinate of a where x is equal to 1. So we're dealing with differentiation again. dy over dx was equal to 2x to the power of 3 plus 2 over x squared, where x is equal to 1. So x is equal to 1. When we plug that in, you will get 2 plus 2, which is 4. And just the rate of change has this formula. So dx over dt is equal to dx over dy. So it's like the reciprocal of what we have there. So 4 would be 1 over 4. And we're given, for dy over dt, we're given the rate of change is 5 units per second. So 5. So 1 over 4 times the 5 is our answer for 5 over 4.